G.2, recurrence relation for Mergesort. We complete the merge step. Given two ordered arrays, we derive the merge operation, combine those two arrays, and get a one bigger sorted array. And we know if we can do that operation, then we can get a whole array sorted, divide and conquer, do in pieces, right? So in that way. But for this video, so we want to look at the recurrence relation because we want to estimate the worst case efficiency. We will go the worst case efficiency. We want to make that big theta of n log n. Yeah. So let's start. Yeah. All right. So in order to derive the recurrence relation for the merge sort, so let us use a diagram to, based on this diagram, we'll try to set up the recurrence equation. Yeah. To estimate the worst case efficiency. So let's draw original array like this. There are n elements. Then we need to use a function to represent running time complexity. Here we use T of n, this function. The problem size n, T of n. Yeah. And we can use the number of comparisons here. Yeah. So as we do usually, we do in this way. Yeah. Then we make even split. For the merge sort, we do even split. So we have pretty much two subarrays like this. Yeah. The first one, divide and conquer. When we conquer, we can call the function recursively T of n over 2. The size reduced by 1/2. Yeah. So that's the cost to conquer the first subarray, to make the first subarray sorted. So what is the cost to conquer the second subarray? Another T of n over 2. Yeah. But after that merge step, we need to combine the results of two sorted subarrays to get one sorted whole array. Yeah. So that combined step, we need to pay some cost. How much is the cost we should pay? Right? Yeah. For the worst case, n minus 1, right? N minus 1, the total number of elements minus 1. Worst case. Yeah, but minus 1, we can just use n for simplicity. Yeah, because that minus 1, it is very easy. When we do something extra, we need to pay that cost, right? It's very easy. We will pay a little more. So that minus 1 cannot save us much. Yeah. So that's why for simplicity, we just use n. Yeah. Now we can write our recurrence relation in this way. Initial condition, very easy. If we have one element, no comparison needed, we already get it sorted. Two comparisons, we only need to do one comparison. We can get it sorted. So we have this initial condition. After that, then to solve the whole problem, we have this expression, right? But when we do the split, we conquer, we combine. We conquer two subarray, we pay this much, and then combine, we pay this much, adding together. So we get this whole equation. Yeah. All right. So now, after we derive this recurrence relation, equation, whatever, yeah, how do we solve it? How do we estimate the solution function? That's our next step. Yeah. So we will use two ways to do it. Yeah. The first way, we solve it mathematically. The second way, we will use a theorem to find a solution. Yeah. All right, so the first way, consider a simpler case of this. Okay, yeah. What's the simpler case? So look at here, n over 2. Remember, we need to split the current array many times. Split, split, split. Every time when we do split, we divided the current array by 2, the size by 2. Okay? When we do that, we do division by 2 operation. To make that division by 2 operation as easy as possible, the simplest case we have is n equals power of 2, 2 to the kth power. If n is power of 2, then we can always do division by 2 to get an integer quotient, right? So that's why we make that assumption to make our formula computation as easy as possible. Yeah. All right. Then we plug in, so we get this new expression. After we get this new expression, how do we solve it from here, from this point? You need to explore the structure. You need to try to reveal its inner structure. So that is important. Yeah. So how to do that? You need to do transform. You need to have some experience. When you see the structure like this, you have some idea how to do the transform. Yeah. So here, based on my experience, I think we should do division method. We need to do division, both sides of the equation, divided by some special number. Yeah. That special number is 2 to the kth power. So that's, based on my tuition, my experience. Yeah. Why is that? Because after that transformation, so you will see we get this new expression. In this new expression, you can see something very interesting. Yeah, so what's that? The two fractions have similar structures, right? They have the similar structures. Okay? Yeah. Before we do this division, it's hard to see similar structures, right? Can you see similar structures for the t recursive function calls? We cannot see immediately, right? Now, after we do this operation, we can see, oh, there is some similarity in these two fractions. Yeah. So with that, now we can do some special thing. We define a new function, because with this structure, can we define a new function using this structure? If we can do that, then we will get a better view. We can see this question in a new way, and we can see its solution better. Yeah. All right. So the new function, we define g. We introduce a new function, g of k equals this structure, whole structure, the fraction, t of 2 to the kth over 2 to the kth. With that, then you can see we simplify the original recursive equation. Yeah, we simplify it. Yeah, so that's the what we have so far. Next, we will use substitution method to get a solution. So how to do that? Here, to do that with the new function, we simplify the original equation to this. G of k equals g of k minus 1 plus 1. See? Because these two fractions, we can use g function to represent. How about that? Can you see this new function much simpler than the old one? But we also need to get the initial condition. G of 1, so you're plugging 1 here, so 1 here, 1 there, so you get t of 2 over t over 2, right? 2 to the first 2. T of 2 is 1 over 2, so you get a 1/2. G of 1 equals 1/2. All right, so with that, now let us solve this new recurrence relation. So let us apply it on g of k minus 1. It equals g of k minus 2 plus 1. 1 plus 1, so we get this 2. Okay, so we can keep going. But this time, how do we envision the last equation we get? How do we see that? Because for things like this, some students may get lost. So we don't know what is the end point. Okay, we cannot predict. Here, let me point out a method we used multiple times before, invariant method. Try to get some invariant quantity, and we use that to guide us to go through the long tunnel and reach the end and see the light at the end of the tunnel. So that's what we are going to do. So what is that invariant here? Size plus the constant term. Size, what's the size number? This is size number, the number inside the parenthesis of the function. What is the constant term? The 1. These two numbers adding together equals k. These two numbers adding together also equal to k. Okay? Now, when we go to the end, we need to make sure 1 plus k minus 1 also equal to k. Okay. In that way, using this invariant to guide us long way through the tunnel, we won't get lost. We won't get lost. Okay? So now you can see, after this expression, we know g of 1 equals 1/2. So if we plug in and do some simplification, so g of k equals k minus 1/2. So we find the answer for the g function. But it's not our original t function. So we need to go back to the t function. That's easy. By the definition of g function, t function here, we multiply 2 to the k to this number. After simplification, we get this expression. Okay? All right. But that's not the one in the form related to the original equation, right? Original equation, we use n as the variable. Here, we use the k as the variable. That's not the same. So we want to write t function in terms of n, not k. So for that reason, the relationship between n and k, n equals 2 to the kth. And k equals log base 2 of n. So with that, we can simplify this t function approximately equal to, approximation because there is 1/2, very small, so we can drop it. Okay, so approximately equal to n times log n, log base 2, n. Yeah. So that's the approximation. But you need to know that is not for the general solution. That is for the power of 2 solution. How do you extend it to the general solution? So we need to do some more work. How do you extend it to the general solution? Okay, yeah. In my next video, I will do that. We will use the recursion tree to do that. Recursion tree to get the general case, not necessarily power of 2, the general n. But there is another way to get that. So not recursion tree, another way to get to that, the general case. Smoothness rule. Remember, in the quiz, I give you 2 questions about smoothness smooth function. Smooth function. Why we need to determine if a function is smooth or not, because we want to apply that smoothness rule. Okay. In next video, we will do it. Yeah. So it is a good result, a good way to find the general solution. Yeah. All right. So let's complete this video G.2 first.